And then finally, I will give a high-level overview of the read and write communication paths between the host controller and the various devices on the memory module. First, I'm going to compare DDR4 RDIMM with DDR4 LRDIMM. On the RDIMM, all commands, address, and control are buffered by the register, here shown as the device in the middle of the RDIMM with the acronym RCD, which stands for Registered Clock Driver. That's the acronym used by the industry. However, as you can see, the data outputs from the DRAM are not buffered on the RDIMM. Therefore, there can be from 1 to 4 DRAM loads presented at the RDIMM connector. This picture shows the front side of the RDIMM. There are just as many DRAMs on the back side. So you can imagine 4 DRAMs vertically placed where I'm showing 1 to 4 DRAM loads. These additional loads degrade signal integrity. Off to the right on the LRDIMM, command, address, and control buffering are similarly buffered by the register, like on the RDIMM. However, the DRAM outputs are also buffered by the data buffers, here shown as the chips with DB. This means that there will only be 1 load presented at the LRDIMM connector instead of 4, like there were on the RDIMM. This leads to better signal integrity on the data signals at the edge connector, also referred to as DQ bits on the edge connector. However, having fewer loads at the connector is why LRDIMMs can be populated into your server with less degradation in performance. Imagine 3 RDIMMs populating a server. That would mean up to 3 times 4 loads or 12 DRAM loads connected onto the DQ path of the motherboard. On the LRDIMM, that would mean only 3 times 1 or 3 loads on the DQ path. Fewer loads, LRDIMM. This concept of RDIMM versus LRDIMM is the same for DDR4 as it was in DDR3. However, we will see later that the DDR4 LRDIMM has a better architecture, improving signal integrity. So now I'm going to start showing the advantages of DDR4 versus DDR3. And here I'm going to be talking about both RDIMMs and LRDIMMs. As far as scalability goes, DDR4 RDIMMs and DDR3 LRDIMMs use the same approach of having a central register device to buffer command and address for the memory module. However, in my opinion, DDR4 load-reduced DIMMs, LRDIMMs, are more scalable than DDR4 LRDIMMs. And I'm showing it here by bringing in the red chips on the top. Okay. As you can see in the pictures, the same central RCD is used in both DDR4 LRDIMMs and DDR4 RDIMMs. Therefore, all of the software used to control the DRAMs through the RCD on a DDR4 RDIMM can be reused for controlling DRAMs on LRDIMMs, hence the scalability. In addition to the register, the LRDIMMs also have 9 data buffers located between the lower DRAMs and the edge connector. The data buffers are controlled through the register and intercept the memory read-write data. In a DDR3 LRDIMM, a completely different buffering device called a memory buffer is communicating with the host controller. Therefore, completely new software must be developed to address the DRAMs on the DDR3 LRDIMM because the register software cannot be reused. Item 2. DDR4 modules will eventually reach speeds of 3,200 megatransfers per second, whereas DDR3 modules have topped out at 2133. Currently, DDR4 is defined for operating speeds between 1,600 and 2,400 megatransfers per second, but there are plans to increase the speed in future products. Additionally, an incredible amount of DRAM memory is possible on these DDR4 modules. DDR4 addressing schemes are prepared to handle 1 terabyte of memory. In DDR3, while 64 gigabyte modules might be realizable, I don't expect any higher densities from DDR3 module vendors. I wanted to get back to comparing DDR3 and DDR4 again. In this case, I want to point out the DDR4 improvements in the signal flow for the DQ bits. These pictures show the DQ data paths. You can see that the DDR4 DQ data path is very consistent from column to column of DRAMs, shown here as vertical path connections. In DDR3, the trace variability from one DQ bit to the next is between 2 inches to 6 inches in length. This means that data arriving simultaneously for 2 different DRAMs at the edge connector will have 2 very different flight times at which the data will arrive at the DRAMs. The modules calibrate out this variability in trace lengths, but signal integrity and performance are compromised. Another benefit to DDR4 is that the training algorithms to remove trace length variability in the command, address, and DQ paths are completely controlled by the host controller. And finally, because these training algorithms are done completely by the host controller and the backside bus is not isolated, the host can be responsible for creating all of the training software, and therefore the training software can be standardized even if different chipsets are used from companies such as IDT. I wanted to quickly show how the DDR4 commands flow from the host to the register, data buffer, and DRAM. For the RCD, the register command words are called RCW, or register command word. You can see here that RCW writes are done directly from the host to the RCD. For reads, an RCW command is sent by the host to the RCD to move the bits into a special multipurpose register in the DRAM, and then the data that has been written into these special registers called MPR registers is read out of the DRAM onto the DQ bus. The data buffer works in a similar way. For the data buffer, the buffer control words are called BCW. You can see here that writes are written from the host via the RCD to the data buffer. For reads, a command is sent by the host to the data buffer to move the appropriate data buffer bits into a special multipurpose register located in the data buffer. Then the register's data is read out of the data buffer onto the DQ bus. And finally, DRAM mode registers called MRS are written to from the host via the RCD to the DRAM. Reading from the MRS registers is also done through the same multipurpose registers inside the DRAM that are used to read out the RCD register contents. In addition, I wanted to point out that you can individually write to the individual DRAM registers and data buffer registers, which is something that was not available in DDR3, which helps with training. Then finally, there's even parity options available to make sure that the signals flowing into the RCD from the host as well as into the DRAMs and the data buffers is valid data. And the difference here is that in DDR3, only the signals flowing from the host into the RCD had parity checking. There was no parity checking for the DRAMs. This slide is meant to intentionally show you how complicated it can become when writing to RCWs and BCWs and MRSs, etc. And I'm going to let Mike and LeCroy go into the specifics of some of these protocols with their presentation, but I wanted to show them to you here. You can see the table below for details, but there are 7 MRS registers, of which MRS 0 through MRS 6 are used to write control information into the DRAMs. Writing to MRS 7, rank 0, side A, with A12, address bit 12 equals 0, writes to the RCWs. Writing to MRS 7, rank 0, side A, with A12 equal 1, writes to the data buffer control words. You can write to them via the host controller. You can also write to them through a serial bus called I2C. So there are different ways of writing. So for example, you may be booting the server, and that would use MRS commands to communicate with all the chipsets on the DIMM. And simultaneously, you could communicate with your, with maybe some kind of debugging software and hardware through this I2C interface at the same time. So again, I'm going to let LeCroy go into the specifics of these protocols with their presentation. So I'll stop here and pass the baton over to Mike.
Okay, thanks a lot, Doug. Well, I think it's pretty clear that these are not your garden variety DIMMs. The DDR4 LRDIMMs are going to be pretty sophisticated devices, definitely a quantum leap in terms of capacity and performance. Definitely there's going to be more complexity and more testing when you're working with LRDIMM. So for the second part of our webinar, I'm going to start by showing you how the Teledyne LeCroy bus analyzer is used to test DDR4. I'll be using some screen captures from the analyzer throughout the presentation to show you, real DDR4 traffic. And this is one way to get visibility to the DDR4 bus. Then we'll focus the discussion around the configuration process. We'll look at some of the different register and buffer commands that get sent at power on. Along the way, we'll see how the bus analyzer can help you troubleshoot problems that might come up. The analyzer uses a slot interposer style probe which sits in line in the DIMM slot. You remove the memory, insert the probe, and then put the DIMMs on top. These are actually UDIMMs in this picture, but some good news. DDR4, RDIMM, and LRDIMM, they're going to continue to use the same connector as UDIMM. So we have a single interposer that can be used to basically test both unbuffered and buffered DIMMs. The blue cable is attached directly to the Keeper 480 analyzer. The interposer probe is self-powered, so it pulls power from the analyzer so it can capture the boot-up sequence when your memory is getting configured. It's going to record the command address and control signals, allowing you to analyze the timing. You can see any state changes, and basically you see every command that gets sent to the LRDIMMs. There's no calibration step, so this makes it quick and easy to get started. The only thing you need to do is to go in through the software and tell the analyzer what speed and latency you're running. You specify these parameters on the left, and then the software loads the exact timing intervals for that DIMM on the right. It can track up to 65 different protocol and timing violations, and it'll actually trigger if it detects any errors in real time. Okay, there's a full-blown timing waveform viewer that allows you to see what violations occurred. This is an example of a timing violation. Here the controller is issuing two write commands that are too close together. You can see all the control signals, the rank, the bank, the full command is decoded. The software uses timestamps to actually show you which commands cause the violations, and you can, of course, do your own measurements. But verifying the compliance at the JEDEC timing table level is really just one part of the feature set here. We have users right now doing DDR4 bring-up testing, functional testing, debugging, real problems at power on. And basically, you can do all this at a much lower cost than using a logic analyzer by using the LeCroy DDR bus analyzer. Okay, let's start by walking through the configuration sequence for an LRDIMM, which starts at power on. You're going to apply voltage, then stay in the reset state for 200 microseconds. Just like DDR3, the host will read the SPD to get the device's operating parameters. The command and address lines between the host and the register are trained first. This is usually initiated with a register command. This just helps make sure that the input side of the register is clocking in a clean signal. This is how all your commands are sent to the DIMM, so it's pretty critical. Next step is to set up the register itself. This is where you see more register commands or RCWs. We'll look at these in detail in a second. The first MRS command that are going to be sent to the DRAM are going to be the typical MRS commands that are needed to set up your CL, your burst length. You still need to do this at the DRAM level, right? You need to send the MRSs, and this is done per rank. Then your normal ZQ calibration commands are sent. These two stages look a lot like what occurs today with UDIMM. But then you need to train the DQ lines on the data buffers. This is, again, initiated by the host with a register command. Really, it's an MPR override read that allows the host to pick one of several training patterns that then gets pipelined from the buffer back to the host over the data lines. So this is really for the host to optimize its receivers, and buffer chips like the IDT0124 have the ability to be tuned independently from the DRAM. There's a large set of special buffer control words that Doug mentioned that the host is going to use to customize how the data buffer operates, mostly to get better signal integrity. Then it's going to move to the full DQS training on the DRAM side of the buffer. This is your write leveling, your read training. Then it exits to normal operation. So definitely the initialization sequence is more elaborate for sure than what we do with UDIMM. It's all done serially for each DIMM. So this could take several minutes with a fully populated system. And again, it's all directed by the memory controller, so this needs a lot of testing. Okay, we're looking here at the different DIMM command, or different commands on the host controller side that he's going to use to set up and operate an LRDIMM. It needs a large command set, primarily to configure the register and the buffer. The first two are standard DDR commands, right, common to UDIMM and RDIMM. For basic operation of the memory, you got your normal read, writes. These are, again, targeted at the DRAM. You still need to write the mode registers, right, to the, with MRS commands, the MRS 0 through 6. Again, we now have this MPR, or multi-purpose register read and writes, that can be sent to the DRAM or to the buffer. Memory guys kind of refer to this as a scratch pad inside the DRAM where you can read and write custom patterns for doing things like retraining and error recovery. The last two sequences are special commands. You've got, again, these are specific to RDIMM and LRDIMM, but you've got your register control words that configure the register, and you've got your buffer control words that configure the data buffers. You know, we'll look at these in a second. Okay, if you're going to be involved with testing and qualifying LRDIMMs, it's really helpful to understand the structure and flow of these commands. You know, this is some of the stuff that Doug talked about, but it bears repeating. Again, standard commands, your write, your refresh, your MRS, they're going to flow through the register to the DRAM. But during initialization, when the host is programming the LRDIMMs, it will send this mode register 7. You know, this MR7 is not considered a normal mode register. With LRDIMM, it becomes a register or a data buffer command. It's always sent to the chip select 0, and if the address bit 12 is 0, it's routed to the RCD. If the address bit 12 is 1, it's routed to the data buffer over the BCOM bus. I'll talk about that in a second, but the key point here is that the analyzer is here. It's monitoring the command and the control lines. So we can see your standard commands. We can see all your buffer commands with the analyzer. Let's stay with the register commands for a second. Again, they flow from the controller to the RCD. These are usually the first commands on the bus at power on. They're used to configure the register. We can set things like the input bus termination, parity checking. They flow through the rank 0 DRAMs behind the register, but because it looks like an MR7, it's ignored by the DRAM. Okay, so MR7's supposed to be ignored, but just by the DRAM. The remaining address bits, you know, your 0 through 12, they identify the control word and basically the payload of the RCW. What does it look like on the bus? This is an RCW. It requires 3 clock cycles to transmit a typical RCW command. Your chip select 0 is low, okay? Your bank group 1 is low. Okay, so this is going to look just like an MRS. Your command pins are going to look like an MRS, where you've got RAS, CAS, and write enable all low, activate is high. Your address pin 0 with the bit 12 contains the address, really 0 through 12 contains the address and the payload of the register commands. So just like a normal MRS, there's a payload that's traveling on the address bus. Okay. All right, so there are 27 register control words. Really more than I can list. This table just gives you a few examples. I'm actually only showing the register address bits. So these bits here are actually the part that contains the payload, right? The rest of the address just identifies which command. So of the 27 commands, about half use a 4-bit payload, and then the other half use an 8-bit word size. These settings are what gets written into the register. One of the main roles of register control words is to tune the output side of the register chip. So these outputs route signals, you know, your command, your address, directly to the DRAM. All right. There are hooks to set the speed, to enable parity checking, turning off chip selects that aren't getting used. There's lots of controls. Okay. So, for example, the RC05 gives us a 4-bit configuration for setting the clock driver strength. This allows the host to boost the clock signal to a higher level, maybe to compensate for a too high stack or a different design, a different raw card. So register commands will play an important part in getting the system configured and really running at the higher DDR4 speeds. All right, another quick example, the RC09. There are several power-saving controls within this register control word. It's a 4-bit RCW. These are the settings. They're configured by the host, all right? So things like the input bus termination can be enabled or disabled. This is similar to ODT, only for the register. So the IBT resistors are actually integrated on the RCD, and they help reduce stub reflections. There's something called CK8 power down mode, which lets the register put the DRAM channel in power down when all the chip selects are idle. Okay, so a lot of controls for the RCW, similar controls for the buffer chips. But getting visibility to these register commands is one of the first steps in bringing up an RDIMM system. So say you're trying to debug a problem, getting the DIMM into a lower power state. Okay, using the bus analyzer, it's possible to trigger on any standard command. Okay. In this window, we're actually seeing the RC09 as it's defined in the spec. So to verify that you're enabling the right bits, there's a built-in option to trigger on the RC, including the entire 12-bit address. For the RC09, all we need to do is set the address bits 4 and 7 to 1. So those bits go high. It's a simple bit mask. Now you're set to trigger on the RC09 command. Okay, so the analyzer triggers. First occurrence, the trigger marker is right here. It's sort of this red line. Again, it's usually a clock or two past the actual event. So floating the mouse over the command itself will basically give you the decoded bits. This is exactly what's getting set, all right, with the power down on IBT on. That's getting enabled. Again, the idea behind this specific command is that this type of termination consumes a little more power but does allow faster power down exit, so it's something that a lot of vendors are going to use. But basically, there's any number of RC commands that you might be interested in capturing. So the analyzer gives you an easy way to do that. All right, so the data buffers have their own set of commands, just like register commands, only they're used to customize operation of the data buffer. They flow from the memory controller through the register to the data buffer itself. Like the register commands, these look like MR7s, where the address lines are really the payload. And as Doug mentioned, the physical link between the RCD and the data buffer is called the BCOM bus. It's a 9-pin control bus that connects the register to each data buffer. I mean, this is how the buffer commands get to the data buffer. It's only 9 pins, though, so the register can't just really pass it through as an MRS7. The register actually has to convert or mux the MRS7 into this BCOM format. So for a buffer command, the RCD maps the 12 address bits into 5 separate data transfers that are basically 4 bits wide. They're sent over this BCOM bus back to back. It looks like this on the bus, where, again, each buffer chip gets a BCOM command similar to this. It takes 5 clock cycles plus a parity cycle to basically complete this command. Once it gets there, the data buffer decodes the command, writes it to its function space, and to complete the command. So it's a little unusual. Like most things from JEDEC, it's a bit convoluted, but it works. And the main function for this BCOM interface is to transmit your buffer control words, but the spec also requires that the register send all read-write commands and MRS information over the BCOM bus, sort of to allow the data buffers to keep tabs on what the DRAM is doing. So again, just to review that one more time, because it is confusing. The buffer command data flow, the host is going to want to change a parameter, typically at boot up. It sends the MRS7 to the register. The register sees that it's an MRS7 with the address bit set to 1. So it's a buffer command. It's not meant for me. It converts it to a BCW and sends it out the BCOM bus to the data buffer. The DB writes it to the function space to complete the command. Okay, so normal commands, your reads, your writes, your MRS, they're going to flow directly between the host and the DRAM. So that's one point that shouldn't be lost on anyone. This is, again, how these LRDIMMs are going to decrease your loading and give you the higher capacity that they're promising. So again, pretty sophisticated, no doubt about it. They're highly configurable. Again, they allow you to customize every aspect of the termination, the signal strength on the DQ lines, in both directions. There are commands to optimize power consumption on the data buffer. There are read-write delays that can be added per data line. So no doubt, a lot of controls. The RCD carries some of this load, but it's mostly on the host controller to get this working. So having an analyzer to get visibility to the host commands is pretty key, both to just get the system configured as well as reaching the higher speeds that DDR4 is promising. Okay, so that is the end of the material that I formally wanted to present. And so by all means, if there are any questions, please type them into the chat box. We'll certainly do our best to answer any questions. Even if they come in later, we'll respond to you by email. Okay, well, here's one question. Someone is asking if it's possible to configure these data buffer chips in parallel, or do they have to be configured individually? And that is a good question. I believe that the answer is that because of the sensitivity to each system, that you're going to have to basically configure each buffer chip individually in a serial fashion every time you boot up. I don't think there's any way that you're going to be able to come up with a series of settings that will work in all environments or in even a given environment from one boot to the next. So this configuration process is one you won't be able to get around as far as the current spec goes. Okay, well, it looks like we haven't got any other questions at this instant. I will wrap up the webinar now. I certainly appreciate you joining us today. Apologies for the audio glitch at the beginning, and look forward to joining us the next time for our next topic, which will be coming out next quarter. We'll certainly be notifying you about that. Thanks again.